we're going to talk about plate tectonics. The plates are actually part of the crust, and the crust is kind of broken into these little, almost like puzzle pieces, so they kind of fit together, and um, and they just float on the upper mantle or on the they call it the asthenosphere. I'll spell it for you. Um, and they just float around on there, and so. Um, that's kind of how we get earthquakes and things like that, and we'll talk some more about that, which are obviously some environmental issues. So here's just some basics about the Earth. The core is the very inner part of the Earth. It's the very, very center, and it's basically nickel and iron. And I've looked at this because people are like, how do they know that? I mean, they've never been to the core. How do they know that? But I guess they can tell based on like the density and the temperature and that kind of stuff. They can tell what what elements are basically like act that way, that or that density and that you know composition at that temperature and that pressure. So that's kind of how they figure that out. The mantle is the middle, and that's the middle layer of the Earth, and that has magma and molten rock, and that's kind of where we get our where the lava and stuff from our volcanoes and stuff that comes from that. Um, and then there's that asthenosphere word that I've typed in for you. And that's just basically the outer part of the mantle, and that's the part that the plates are actually floating on. And then the lithosphere is actually the crust, and that's what's made up of the plates. Those puzzle pieces, basically, that are floating on that asthenosphere. I don't know why I have trouble pronouncing that. So then we have these places called hotspots, and we'll get a little more into this a little later, but basically these are places where plumes of hot magma will well upward from the mantle, and this is where these areas of mantle or these bits of magma can actually reach the surface. And so you can see here, we have these hotspots right here. And these are places basically where the crust is really thin, or somehow there's a way for that magma to get to the front or to the top. And then here, we'll discuss this later too, but this is basically, they call this the ring of fire. And you can see the plates here, like these red lines. These are basically the plates. Okay, so they're like little puzzle pieces. They kind of fit together. And that's kind of, our Earth is made up of those. So basically the world's continents were, at one point, they were joined in a single landmass Pangea. I'm sure you guys have heard this before. I like this picture because it kind of shows where our current like political boundaries, where those would have been in Pangea. And it's kind of interesting because they actually call it the theory of plate tectonics, which means it's not like a theory like, oh, this might be happening. But it's basically like there's no way to actually test it or prove it because it's not like you can there's just there's a bunch of data to back it up, but you can't actually like zoom out of the Earth and see the plates. We see fault lines and things like that, which we'll talk about in a second. But and we can see how these land masses kind of fit together. Like I always thought it was cool how like how Africa and South America just fit together so perfectly. I always thought that was really neat. So here's our plates again. This is a little more like a cartoon version, but the plates are all different colors, so you can kind of see them a little better. And this is just kind of, they're just showing you where the plates are. And these plates are constantly moving. They're not really fast. It's not like an escalator where, or one of those like moving sidewalks at the airport where, you can feel it moving. They move very, very slowly. So oceanic plates, this is one of those times in science where it makes sense, and the word sounds like what it is. So the oceanic plates are ocean plates, plates that are over the oceans, and continental plates are plates that are beneath basically the land masses. So I kind of like that when science makes sense like that. So the oceanic and the continental plates, this should say just the continental plates arise above the oceanic plates. So the weight of the ocean causes basically the oceanic plates to be a little, they are pushed down a little bit, and the land is not really as heavy as all of that ocean. And so when an ocean plate and a continental plate come together, the oceanic plate is usually the one that will go underneath, and the continental plate will kind of go above it, or yeah. And so you can see there's some magma coming up here in a volcano or whatever. So this would be a continental plate, and this would be an oceanic plate. And then where they come together, you can see how it's a little deeper there. That's where the trenches are. So anytime you see a trench like the Marianas Trench or anything like that, that is the where two plates meet, and that's why it's so deep there. And then basically, yeah, it's just saying that they're floating on the asthenosphere or the mantle. So we have this thing called seafloor spreading, and this is kind of interesting. As oceanic plates move apart, magma forms new crust on the seafloor and the boundaries between those plates. So like here, we have this magma, and it's coming out, and it's basically like forming new ocean, brand new ocean floor right here, okay? And that's pushing these two plates kind of away from each other, and we're getting this new bit of ocean right here in the middle, okay? I used to think when I was, when I first learned this stuff, that meant that the radius or the diameter of our Earth was obviously increasing, right? Because if we're getting new crust all the time or new ocean, and these are spreading apart, then obviously, our Earth must be getting bigger. But that's not true, right? We also have these places where this crust is like kind of sinking back in when they meet other plates, and so it kind of evens out. And so basically the Earth stays the same diameter the whole time. So I just wanted to pass on that misconception of mine that I had to you, that way that you guys don't have that misconception as well. But what is neat about this is there's all these elements, these metals and stuff that we talked about that were in the mantle and the core and things like that. And this is a way to get those elements to the surface so we can get more of those elements. Because, let's say there's a certain amount of copper here, but there's some, trapped in the center of the Earth that, maybe we're not, we don't have access to. That's a plate. That's a way that it gets to the surface. That's the way it brings some of these elements to the surface. Well, at least the surface of the crust anyway. Maybe not. They don't just like float to the surface of the ocean. You're not going to find like balls of silver and copper and lead like floating on the surface of the ocean, but it brings it basically to the surface of the crust. So then we have this thing called subduction, and this is kind of what we were talking about. When a ocean plate meets a continental plate, the ocean plate will go underneath, and they call that subduction. Okay, and then it kind of melts a little bit, and then it comes back up, and it, it's a cycle kind of. Some people even call it the tectonic cycle. So then we can talk about volcanoes. And what's interesting is I always thought this was really, really cool. So, for example, this is how Hawaii formed, and this shape of Hawaii is pretty standard actually for these ocean chains, and it's because there's some tilt to the Earth and some rotation. So as the plates are moving over the hot spot, so for example, this would be like the Big Island in Hawaii, and this would be like the last one. As it's moving, it's actually moving in a straight line, but because of the rotation and stuff of the Earth, it ends up forming this like curve a little bit, this like upside down comma shape. Because of that, if the Earth didn't rotate, it would be like a straight line like this. But since there's this rotation factor, it actually causes them to kind of go like that, which I thought was really cool. And that's why the Big Island, right, of Hawaii has an active volcano on it right now. And then you can see the islands kind of get smaller as they go away, and that's because they're the older islands. So like Kauai is much older than the the Big Island of Hawaii. And the reason the Big Island is the Big Island is because it's the most current one. What is the rate of seafloor spreading? I want to say it's like millimeters. I don't have the like exact like how fast it happens memorized, but it's really really slow, like millimeters over like long periods of time. So it's not super super fast. Um, and so like a lot of people are like, oh my gosh, California's gonna fall into the ocean, whatever. It's not. You know, like that kind of stuff with the plates, it's really 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 slow. Um, not enough for us to like notice it. That's why they're saying like, see, Hawaii is zero point 0.8 millions of years to the present, and then Kauai is like 3.8 to 5.6 millions of years. So, you know, it's going that distance in, you know, like 5 million years. So it's really, really slow. Um, but I always like to talk about this because I just think it's so neat that that curve pattern and the way those islands are formed. It's just, for me, plate tectonics is not like my favorite subject, but when I heard about that the first time, I was like, wow, that is so cool. Anyway, that's my nerdy science self. So now we'll talk about divergent plates. So we had those convergent plates, right, like subduction where they hit each other. So now we can talk a little bit about divergent plates. And now I couldn't find a good graphic for divergent. So this one shows a few different ones, but it has a divergent one right here. And this is basically that seafloor spreading. Those are divergent plates because they're moving away from each other, right? If you've got these two plates are moving towards each other, and these two plates are moving towards each other, they've got to be moving away from each other at the other end, right? So that's kind of what's going on there, and that's what's causing that seafloor spreading. And then here's some more convergent plates. I really didn't organize this very well, but that's okay. So convergent plates are, again, where those plates are coming towards each other. We already talked about this. The oceanic plate will always slide under the continental plate. And then that's what gives you these. You see how these, we have like ocean or mountain ranges kind of near the coast. Like if you think we've got the Rockies, right? They're pretty close to the coast as far as like, you know, the size of the earth and the size of the continent. And then we have the mountain range on our side, the Appalachian Mountains, right? Those are also fairly close to the coast, and that's because of that that where we're getting these two coming together, and it's going to cause that mountain. So basically, like if two continental plates meet, then you're going to get kind of like a mid-continental mountain range. So if they come together, like this was a divergent one right here, but if these two came together, they would come together and they would smush and create like a mountain. It's almost like a car accident, like a smushy car accident, where like, you know, the fronts of the cars kind of come up a little bit. That's kind of, that would be a mountain. Yeah, subduction would be a convergent plate collision, because convergent is whenever they come together, and divergent is when they separate. So since in subduction, the oceanic plate is going under the continental plate, but they're coming together, that would be a convergent plate collision. And then we can have these transform faults. So we talked about how they can, you know, like bump into each other almost like a car accident, and they can separate from each other, but then they can also slide back and forth, excuse me, against each other, and that's where we get a lot of our earthquakes, is these the sliding back and forth. And you can see this is actually a transform fault right here, and the earthquake is when those plates are kind of sliding back and forth against each other. So here we go. Here's some more faults. And basically these fault zones, they call them fault zones, are large places where rock movement has occurred, and it's causing these kind of like mountainy kind of fracture areas. Okay, so now let's talk about earthquakes, because in environmental science, right, we had to do all that was basically earth science, and we have to understand that stuff in order to discuss earthquakes and tsunamis and things like that, which is really what environmental science focuses on. So earthquakes are when the rocks of the lithosphere, which is the crust basically, rupture unexpectedly along fault lines or where those plates connect. Okay, so you can see some results of earthquakes. And then these fault zones that we just showed on the previous slide, these are areas where we're going to have, we're more likely to have earthquakes. And so the epicenter of the earthquake is basically the center of the earthquake. So, you know, if you've got your, let me see if I can get a pen here. Okay. So if we have our earthquake and this is our epicenter right here, it kind of moves out in like waves. So it's going to be stronger in this epicenter and then lighter and lighter and lighter as it goes out, because it's these are actually like energy waves. This is, now we're getting into physics a little bit. That's the thing about environmental science. It seems like it puts all the sciences together. And so the Richter scale is going to measure that magnitude. Now, if this is on land, right, you're going to have some major destruction here and less and less and less as the farther you get out. But now if this epicenter is in the ocean, that's going to cause a tsunami, which we'll talk about, which is this huge, huge ocean wave. And a tsunami actually, you know, how we talk about on Earth or on land, this is going to get less strong as you move away, kind of like the ripples in the ocean. Well, a tsunami, it kind of like gathers water. And so it gets actually stronger the farther it moves, and then it's going to hit some sort of landmass eventually. You know, if this is a landmass, and it's going to have this huge wall of water that's going to kind of come over, and that causes huge problems because usually this is ocean water, right? And ocean water has a lot of salt and things like that, and these land plants are not adapted to all of that salt water, and so that can cause some problems on the FRQ that you guys have been talking about this week and next week. They talk about salinization. So if you've got like farmland here, and then all this ocean water gets on this farmland, it's going to deposit a bunch of salts on the land, which can cause some problems because then the dirt is basically too salty, or the soil is too salty for plants to grow. So it can have these like wide-ranging effects, which is why we even care about this in environmental science. So the 2010 Haitian earthquake, the anniversary of that was just like a couple days ago. It was a 7 on the Richter scale, and it killed more than 200,000 people. They said they'll never actually know how many people were actually killed from this earthquake, because a lot of them were buried in like mass graves because there were just so many people that died. They just buried a bunch of people in like one big, you know, a mass grave. And so, you know, they didn't really count them. That wasn't their, you know, their focus at that point in time in Haiti was not, you know, counting how many people they were throwing in those mass graves. It was just, you know, trying to get their lives back together. So, and the reason I bring this up is because one of the things in environmental science is they talk about current events. So, like, I think it was last year or the year before, they had an FRQ like all about the Haiti earthquake, and then they had another FRQ recently that was about the tsunami in Japan. And so these like large scale disasters, or you know, things that are going on like the fires in California, those are kind of things that you guys should just kind of pay attention to. And a good way to get those, so this is kind of off topic but not really, a good way to kind of get an idea of these types of things is maybe like on Facebook, which is probably a place that you guys are already at anyway. Follow maybe like BBC Nature, or like National Geographic, or you know, some places like that. There's a group called I really, 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 really love science, except there's another word that they use for that on Facebook that has really good science news, and just kind of like follow a couple of those pages, and then their stuff will start showing up in your news feed, and just, you know, like it every so often. That way you know, they keep showing up in your news feed. They have those algorithms, you know, if you don't like stuff or whatever, that you don't see it as often. But that's a good way to just kind of get that stuff in there. If you guys are on Twitter, you can follow National Geographic, NASA, groups like that. And then you can get some of that science news like in your Twitter feed or whatever, and then you're getting those current events kind of exposed to them in a relatively painless way without having to actually like read a newspaper or something like that. So that's kind of a way that I would kind of suggest at least getting some current event, because a lot of times those current events then show up in FRQs. So here's that ring of fire that I was telling you guys about, and it's basically I used to do an activity with my students where we would plot the location of earthquakes and volcanoes, and to kind of not prove, but kind of show evidence for this plate tectonics theory. And literally the volcanoes are all up and down this ring of fire. Okay, they're all here. And that's a plate boundary. Okay, and then the volcano or the earthquakes are all along the plate boundaries. I don't have them all memorized, but I know there's one like kind of around here, I think. And so when you plot those earthquakes and those volcanoes on a map, it actually almost makes the shape of the different plates, because that's where they happen. You're not going to find a volcano or an earthquake like right here. It's very, very unlikely, just because of the way the plates are located and the way the plates work. So now we'll talk a little bit about mining. Not a ton. I'm not going to go over like your site has a lot of good information on mining, so I'm just gonna kind of go over a little bit of it. So we use mining obviously to get fossil fuel energy, usually coal, but we can mine for other things. You can mine for uranium, you can mine for copper, you can mine for aluminum, you can, any sort of metal you're going to mine for. But coal is the one that they like to focus on a lot. And the reason for this is because we used to use coal a lot for energy. We don't use it as much anymore, although I think Donald Trump, part of his campaign was reinstating coal jobs, I want to say. I tried not to pay too much attention to his campaign because it's hard to keep track of all the things that he says. But I think I remember something about coal being one of his things. But basically, we talk about a lot in environmental science because mining causes some major environmental issues and also some health issues. So, and one of the health issues is something called black lung, and that's kind of like the common name for it. The real word is coal workers pneumococcus, or I can't even say it. CWP, black lung. And basically, you get it by inhaling coal dust, and you get this coal dust in your lungs, and it's really bad. You start coughing up black stuff, and you're really, really sick. It's almost like you have a lot of the same symptoms as like a smoker that's been smoking for a long time. You can get lung cancer, all sorts of stuff. It's really bad. Most of our mining right now is what we call surface mining. And this is where we're actually like mining on the surface. So, this is the surface. We're actually digging straight on the surface. Whether we're just digging and we're creating these, sometimes they call them quarries, these big holes in the earth like this. Or in some places in the Appalachians, they actually they do this thing called mountaintop removal, where they actually take a mountain and they put a bunch of explosives and they literally like blow off the top of the mountain to get to the coal in the middle, which obviously has some huge environmental effects if you're blowing off the top of an entire mountain. You can look up some pictures of it. It's pretty interesting. All the mountains are like flat like this. John Grisham has a really good book about it, but I don't remember what it was called. But it was a good book. It was very good environmental science, but it was interesting because it was John Grisham. And so surface mining obviously is going to have more environmental impacts because it's we're actually dealing with the surface. We're not keeping the surface intact. We're completely destroying the surface environment. If there's trees here, you know, there's not trees obviously here anymore. If there were trees on this mountain, you know, there's not trees anymore. There's not even mountain anymore. Okay, so that's going to cause huge environmental impacts. Um, and also like the aesthetics of the environment is going to cause huge impacts. And that's most of our mining, right? And then the other 31% of our mining is underground mining. The good thing about underground mining is that, you know, you're basically leaving the environment intact. You're creating this little tunnel, and then you'll create like a, you know, like a, usually they make these like little rooms basically. The newsletter this week had a picture of some miners in one of these underground mines. You're going to have substantial environmental impacts still, you know, because you've got this area around here. Sometimes this can light on fire and cause explosions, you know, which is obviously not super. And then the 50% of this of the ground must be left in place to support the roof of the mine. So you just can't, you know, dig this, keep digging it forever, right? Because you'll dig too much and then it'll basically collapse on you. Kind of like if you've ever been to the beach and you try and dig like a, you know, you try and dig like a tunnel, or you dig, you know, you make like a hole in the ground like this. Have you guys ever done that? You make like a hole like this, and if you dig too much this way, then this part just kind of collapses into your hole. It's the same kind of thing. And so that's why they like to do surface mining, because they can get everything out, and they don't have to leave anything in place. But then, you know, the surface mining has more substantial environmental impacts. So it's kind of a, I wouldn't say it's a wash, but there's negatives with both. So here's strip mining. This is kind of what I was trying to show you a little bit. You can see, right, these were mountains, and now they're like flat, right? Let me see if I can get a different color. Okay, so you can see that these, you know, this mountain is like totally flat now, right? And they've completely destroyed the ecology of the region, right? Because this is what it probably should look like, well, except for this house. And then now this is what it does look like, right? So this would be like before, and this would be after. So you can see it's totally different. You know, you're not going to find animals living here, or, you know, you don't have any trees or anything like that. I mean, it's completely changed the ecology. I bet this area here is significantly hotter than this area because, you know, we've got the trees for shade. I bet this area gets more rain than this area because you know, you've got that water cycle is still in place right here. Then you have over here, this is probably very dry. I mean, it just looks dry from the picture. So, you know, just those huge environmental impacts just like that without me even kind of knowing anymore, just looking at the picture. So they use dynamite basically to break the surface. It's obviously going to destroy the ecology of the region, including the groundwater and the waterways, right? Because if there is a waterway here, like for example here, all of this stuff that's been here, the dynamite, all of that, it's all going to run off into this water and cause, you know, you're going to have increased sediments. A lot of times they have what they call like acid mine drainage that's going to get in here and cause problems with these waters. A lot of times, see, here's another one. A lot of times the companies that do this get exemptions from the Clean Water Act, so they don't have to, you know, clean up after themselves, which is kind of unfortunate. And then obviously you're going to have more erosion here because what do plants do, right? One of the things that plants do is hold the soil in place. But if you don't have any plants, you're obviously going to have more erosion. And so then, like, look at this steep slope, right? You're going to have lots of sediments coming down the steep slope. It's going to come down this way into this waterway and make it into here. And I'm sure this isn't the end of it. I'm sure it goes somewhere else. So, you know, these are these like, you know, it's not just the erosion, but then you're going to have the erosion and the runoff and all of that. So it kind of builds on itself. One of the things that I read about in one of the textbooks that I read was this Massey Energy Company. They actually violated the Clean Water Act on over 4,500 occasions, and they basically only had to pay $30 million, which for a huge energy company, $30 million is like nothing. And so, like a lot of times when you guys are writing on your discussions, oh, well, let's just make them pay a huge fine. Okay, they've got tons of money. They made way more money than they lost doing this. Okay, like the BP oil spill. They BP has so much money that any fine that they had to pay because of that oil spill was just like a drop in the bucket, right? It was like nothing. Um, so, you can establish these fines, and that's, all well and good for some, but, these huge, huge companies, it's nothing to them. They're like, okay, you know, they kind of plan for that. We're probably going to have to pay a fine at some point. So, you know, they kind of plan for that. And then coal power. So I know in the last course, I believe you guys talked a lot about the different types of energy and coal versus nuclear versus natural gas, that sort of thing. But basically, a typical coal power plant will burn about 8,000 tons of coal a day, which is, a large amount of coal, which is, why they have to like basically blow up mountains to get enough coal to run these things. And it releases about 20,000 tons of CO2 and 800 tons of SO2. Both of these are greenhouse gases and air pollutants. Okay, so this is a really large amount of greenhouse gas just being released um, from one of these power plants. And then this waste, right, is 1,600 tons of ash, and this waste, it has to go to a special landfill. You can't just take it to the regular landfill. You have to take it to a special landfill that's has special lining and that kind of stuff, to make sure, because you've got this ash, so it's kind of flammable. It's not, you don't want that leaking into your groundwater. The only good thing about it is that at least it takes up less space than the coal did originally, because the ash is usually a smaller amount. But that's really the only good thing about the ash. Um, so these are huge, and this is the CO2 that is released just from burning the power plant. It doesn't include the CO2 from actually doing the mining, driving the coal to the power plant, driving the ash to the landfill, all of that sort of stuff. It's not including that part. It's just the actual burning of the coal at the power plant. Um, but so it's not a super clean energy source. You can see this, right? If you look at old pictures of like London, um, during the Industrial Revolution, it was really, really bad. You couldn't see very well, and it was all, because they used this coal power. So um, that's the last slide I have for you today.